Today we will discuss about what is meant by torque and angular momentum and rotational and translational equilibrium. Regarding equilibrium we will discuss. Okay. So first of all we will discuss what is meant by torque or moment of force. Moment of force or torque. Torque is very simple sentence. We can say that it is the turning effect of force. Turning effect of force is known as torque. So have you ever thought that whenever that door is there, the handle of the door is kept far away from the hinges? Whether you thought that why it is kept far away from the hinges? You can keep anywhere, you can keep near to the hinges also. Why it is kept far away? You can try to open the door. So if you are applying force on the door near to the hinge, you have to apply a larger force. And instead of that, if you are trying to open the same door from far away from the hinge by applying a force, less force is required. Okay. So even though the same force if you are applying, what happens? You cannot open the door if you are applying the same force near to the hinge. But with the same force, you can apply or you can open the door if it is far away from the hinge. That's because of that reason only the handle of the door is kept far away from the hinge. Okay. So in that case, what happens is that not only the force is responsible, at what point from the axis of rotation, how far that distance, it also affects the turning effect of force. Okay. So we can define torque as torque is equal to, torque is represented by the letter tau, Greek alphabet, that is equal to force into perpendicular distance from the axis of rotation to the line of action of force. Perpendicular distance from the axis of rotation to the line of action of force. Perpendicular distance for torque we can define as force into perpendicular distance from the axis of rotation to the line of action of force. That's why I told you in the case of door handle is kept far away because perpendicular distance is more. So if distance is more, with less force it can produce more turbulence. Okay, that's why we are defining torque. Torque is equal to force into perpendicular distance. Okay, but in the case of a particle, how can we define torque? Torque acting on a particle. In the case of a particle, we can define torque as torque is equal to R cross F. Vector torque is a vector quantity. It is defined as R cross F. What is R? R is the position vector of the particle. And F is the force vector. Okay. So we can define torque is equal to R cross F, or magnitude if you are writing R into F into sin theta into unit vector n, where unit vector n you can write as R magnitude of R into magnitude of F into sin theta into n cap, where n cap is a unit vector perpendicular to the plane containing R and F. Because in the case of vector product already we discussed in the previous videos, you might have seen that in vector product, that is a vector will be perpendicular to the plane containing the vectors. Okay. So in rectangular components, how we can write that we can see. Rectangular components. how we can represent torque in rectangular components. So here R, the position vector can be written as xi plus yj plus zk, and force can be written as fxi plus fyj plus fzk, where fx, fy, fz are the components of force along xyz direction. So we can find torque as torque is equal to R cross F, and that is equal to the determinant I, J, K, X, Y, Z, Fx, Fy, or that can be written as I into that row and column should be avoided, then we can write y into fz minus z into fy, y fz minus z fy, minus j into x fz minus z fx, x fz minus z fx, plus k into x fy minus y fx. So you can see that torque is a vector quantity, and those who are having doubt how we calculated, you can go to the video regarding the vector product, how to calculate vector product of two numbers. Okay, so this is about the rectangular components of torque. Okay. Angular moment or moment of linear movement. Angular momentum or moment of linear movement. In the case of linear momentum, it is a measure of the translatory motion of the object. So in the same way, we can define angular momentum is the measure of the rotational motion of the object, and it is defined as wherever moment is there, there will be position vector cross that term. So in the case of moment of force, we have written R cross F. So here it is moment of linear momentum. So how we can define angular momentum is represented by the letter L. So angular momentum is equal to moment means position vector will be the R cross linear momentum. Linear momentum is represented by P. So we can write R cross P. So this is the angular momentum of particle. Okay. So that is what is the physical significance. It gives a measure of the rotation motion of the object. And now, what would be the unit of angular momentum? From this you can write the unit. No? What would be the unit? What is the unit of R? Unit of R is, you can write SI unit. Unit of R is meter. And P, what is the unit of momentum? Momentum is kilogram meter per second. So unit is kilogram meter square per second. So the SI unit of momentum, angular momentum is kilogram meter square per second. Similarly, what is the unit of torque? Torque, you have written torque is equal to R cross F. So you can write SI unit. What is SI unit of torque? SI unit of torque is equal to SI unit of R. What is SI unit of R? R is the distance, position. No? SI unit is meter, and F unit is Newton. So we can write Newton meter. Or if you want, you can write it as joule also, not a problem, because Newton meter can be represented also as joule. So SI unit of torque is Newton meter or joule. So we can say that two examples of two two quantities having same direction. For example, in the case of this torque and work energy all are having same unit and same dimension. Okay, is it clear? So this is all about angular momentum and torque. Now we can represent angular momentum also in rectangular components. Angular momentum in rectangular components. Already we know that L is equal to R cross P. So position vector can be represented as xi plus yj plus zk, and momentum can be written as pxi, where px is the x component of momentum, pyj, it is you should be very careful when you are writing. It is not p into x, it is p suffix x. Okay, pxi plus pyj plus pzk, where px, py and pz are the components of momentum along x, y and z directions respectively. Okay, so if we are substituting here, what we can write? L is equal to xi plus yj plus zk cross pxi plus pyj plus pz, or in determinant method we can write ijk, that will be written in the first row. Next, whichever component is component of first vector will be written x, y, z. Then next px, py, pz. So that can be written as the row containing that element should be avoided and column also should be avoided. So this will be avoided. So y into pz minus z into py, y pz minus z py minus j into x pz minus z px plus k into x py minus y px. So like this we can find angular momentum if position vector and momentum are given in vector form. So we will get the angular momentum, or we can represent angular momentum in rectangular components. Okay, is it clear? Relation between torque and angular momentum. Relation between torque and angular momentum. Okay, so we know the relation L is equal to R cross P, that already we discussed, and we also know that torque is equal to R cross P. Okay, so we have to find the relation between torque and angular momentum. So for that we are starting from the expression of angular momentum itself. We are writing L is equal to R cross P. Now we are differentiating this expression. Okay, we can write differentiating with respect to T. We are differentiating this equation 1. We can write differentiating equation 1 with respect to T. But we can write dl by dt. D by dt of L is equal to d by dt of R cross P. Okay, or we can write dl by dt is equal to, we can write it as dr by dt cross P. The rule in differentiation, if we are differentiating first function into differential of second plus second function into differential plus R cross dP by dt. dr by dt cross P plus R cross dP by dt. So what is dr by dt? dr by dt means rate of change of position, rate of change of displacement, and we can write it as velocity. So dl by dt is equal to v cross P plus R cross, what is dP by dt? Rate of change of momentum, that can be written as force. And now this term is 0. Why this term is 0? V cross P is equal to 0. How we can show? What is P? P is moment. So we can write V cross M. Momentum can be written as mass into velocity. So if you are taking M common, V cross V. V cross V is 0. Why V cross V is 0? This can be written as, if you are writing A cross B, how we will write? Modulus of A into modulus of B into sin theta into V. So here two vectors are there, similar vectors, same vectors are there. So what is the angle between those two vectors? Angle between the vectors will be 0, theta equal to 0. So we can write this will be a 0. So this term vanishes. Now what you got? dl by dt is equal to R cross F, and R cross F is torque. So we can write torque is equal to dl by dt. We can write torque is equal to dl by dt. Similar to force, no? Force we are writing rate of change of momentum. Here torque we can write it as rate of change of angular momentum. Okay. Wherever linear momentum, if it is replaced by angular momentum, you will get a corresponding relation. So here torque, linear momentum, sorry, but it is force, we are writing it as force, we are writing it as F is equal to dP by dt. Force is equal to rate of change of linear momentum. So force is replaced by torque. So linear momentum can be replaced by angular momentum. Get the corresponding equation in rotational motion. Okay, is it clear? Torque and angular momentum for the system of particles. So far we consider only one particle, and in the case of a liquid body it contains many particles. So what will happen to what will be the expression for torque and angular momentum for a system which contains many particles? Okay, so let R1, R2, etc. Rn are the position vectors of the particles, and let they are the position vectors of the particle from the axis of rotation. Position vectors of the particles. And let F1, F2, etc. Fn are the forces acting on those particles. Force vectors. What is meant by F1 is the force acting on the first particle, F2 is the force acting on the second particle, F3 and Fn is the force acting on the nth particle. And let P1, P2, etc. Pn are the linear momentum vectors of the particles. can get the first torque. Torque can be written as total torque can be written as total torque is equal to torque acting on first particle plus torque acting on second particle plus etc. plus torque acting on the next particle. And torque 1 can be written as R1 cross F1 and torque acting on second particle can be written as R2 cross F2 because R2 is the position vector and F2 is the corresponding force acting on the particle plus etc. plus we can write nth particle Rn cross F. Or we can write instead of this one we can write summation sigma I is equal to 1 to n Ri cross F. So the total torque can be written as total torque is equal to sigma I is equal to 1 to n Ri cross F. The same way we can write angular momentum also. How? Angular momentum can be written as R cross P. So total angular momentum can be written as R1 cross P1 plus R2 cross P2 plus etc. R3 cross P3 etc. Rn cross P3. So that can be written as total angular momentum can be written as summation we can do sigma I is equal to 1 to n Ri cross. So the total angular momentum in the case of a system of particles we can write by adding each vector. Instead of that we are using summation sigma I is equal to 1 Ri cross P. Okay. Equilibrium of rigid bodies. Equilibrium of rigid bodies. Okay. So in the case of equilibrium means if there are two types of equilibrium in the case of rigid bodies, translational equilibrium and rotational equilibrium. Okay. Translational equilibrium and rotational equilibrium. So in the case of translational equilibrium we can say that a rigid body is said to be in a translational equilibrium if the net force acting on the object is zero. Okay. A rigid body is said to be in translational equilibrium. Translational equilibrium. In translational equilibrium if the net force acting on the body is zero. So it is said to be in translational equilibrium if the net force acting on the body is zero. So if the net force is zero, what happens? We can write net force F is equal to 0. Net force is equal to 0. So we can write its total momentum is rate of change of momentum is 0, or we can write momentum is constant. Or in other words, we can say that mass, total mass into velocity of center of mass is constant. Or we can say that the velocity of center of mass remains constant for an object when it is in translational equilibrium. Okay. When an object is in translational equilibrium, net net force acting on the object is 0. So if the net force is 0, we can say that total linear momentum is constant. That also we can write. So the total linear momentum is constant. Linear momentum is constant. Or other words, we can say that velocity of the center of mass is constant. This is for translational equilibrium. And in the case of rotational equilibrium, this is for translational equilibrium. Okay. Now we can see about rotational equilibrium. So in the case of rotational equilibrium, an object is said to be in rotational equilibrium. Object is said to be in rotational equilibrium if the net torque acting on the object is if the net torque acting on the object, if it is 0, that object is said to be in rotational equilibrium. So we can write net torque is equal to 0. If net torque is 0, we can write dl by dt is equal to 0, or we can write angular momentum is constant. Rate of change of angular momentum can be written as torque. So we can write, so if an object is said to be in rotational equilibrium, either its total torque acting on the object is 0, or we can write the total angular momentum remains constant. Remains total angular momentum remains constant. Then we can say that object is said to be in rotational equilibrium. Okay, is it clear? So here these are the two examples for equilibrium, that is rotational equilibrium and translational equilibrium. So here we can see that here what is the net force in this diagram? We can see net force is equal to, both forces are acting downward direction. That is, here a load is balanced in the center with the help of, here two weights are hanging. Okay, two objects are there hanging. Because of its weight, two forces are there. Both are having same masses. So net force can be written as both forces are acting in the same direction. So net force is equal to. And here what is the torque? Here what happens, this object will try to rotate it in anti-clockwise direction, and this object, because of its weight, it will try to rotate in clockwise direction. Since both are having same weight, we can write what we can write, and here in the case of this one, anti-clockwise direction is taken as positive and clockwise direction negative. Anti-clockwise positive and clockwise direction, rotation negative. So here we can write force into perpendicular distance. What is force is F. F into perpendicular distance is D, and this will be minus F into D. That is equal to C. Why? If both are same, so what happens here? Net torque is equal to, net torque is equal to 0, but it has net force. Okay, so this is an example of rotational equilibrium. That is, in the case of this example, you can see that net force is not 0, but net torque is 0. So this is an example of rotational equilibrium. Okay, rotational equilibrium, because net force is not 0, but net torque is equal to 0. Both are having same weight. If weights are different, what happens? If this is W1 and this is W2, in that case, net torque can be written as if W1 and W2 are the weights. Here if we are writing, okay, then we can write W1 D distance also if it is not same. So we can write W1 D1 minus W2 D2. Okay. And here distances we are considered them as same if they are different. And D1 and D2 are the perpendicular distances. Perpendicular distances from the axis of rotation. Okay. So in that case, we can write W1 D1 minus W2 D2. That cannot be. It will not be equal to 0. How we can write? That will be equal to the net W1 D1 minus W2 D2, and if it is in equilibrium, we can write that is equal to 0. W1 D1 minus W2 D2 equal to 0, or we can write W1 D1 is equal to W2 D2 if it is given that if it is in equilibrium. If it is in rotational equilibrium like that, if it is given, not necessarily that if distances are different also, anti-clockwise momentum and torque and clockwise torque should be equal. Okay, this is example of rotational equilibrium, and here we can say that second example of translational equilibrium. So two equal and opposite forces separated by some distance, I think that is known as couple. Okay, couple. This couple also produce only turning effect, no translatory motion, because here you can see that net force, both forces are acting in opposite direction. So net force is equal to 0, and both force will try to rotate the object in the same anti-clockwise direction. So torque can be written as, if this distance you are writing it as D1 and this distance D2, so you can write F D1 plus F D2, or torque is equal to F into D1 plus D2, where D is the perpendicular distance between the forces. Okay, so torque can be written as force into perpendicular distance in the case of couple. Okay. So when you are opening the lid of a bottle, where you are applying equal and opposite force, which produce only turning effect, which will try to open that lid. Okay, so two equal and opposite forces separated and acting not along the same line of joining, acting at some distance, that is known as couple, and this couple produces, here net force will be 0, both forces are acting in opposite direction, so net force acting on the object is 0, but it will produce turning effect because both force will try to rotate the object in the same anti-clockwise direction. So torque can be written as S into D. So here you can see that this point origin doesn't matter, whether you are taking here, anywhere, it doesn't matter. Torque depends only on the force and the perpendicular distance between the forces. Okay, is it clear? So these are all about rotational equilibrium and translational equilibrium. Now we will discuss just 2-3 about what is meant by stable, unstable and neutral. Stable equilibrium, unstable equilibrium and neutral equilibrium. Okay, so what is meant by stable equilibrium? In stable equilibrium, if an object is in stable equilibrium and if we are applying, if the object is displaced, slightly displaced from its position, after some time it will come back to its original position. That type of equilibrium is known as stable equilibrium. So in stable equilibrium, potential energy will be minimum, so that once it is displaced, it will try to come back to get minimum energy, so that it will come back to its initial energy, that is initial status. So here in the case of stable equilibrium, for example, if you are considering the case, an object is in a vessel like this. Okay, here the object is like that. if you displace that object, what happens? It will move. Either if you are pushing that object upwards, so it will go upwards. Again, it will come downwards, and finally it will reach to the same position. After some time, it depends on how fast, how far you are displacing that object. That's why I told you it should be displaced slightly. If you are displacing it larger, what happens? It may escape from this also. Okay, that's why when the object is slightly displaced from its equilibrium position, it will come back to that same position once after some time. Okay, that type of equilibrium is known as stable equilibrium. Okay, so it will come back to its own position. Okay, so here once when it is displacing, its center of mass lies above. Okay, above the actual mass. And in the case of unstable equilibrium, which is very easy to say, if an object is here, what happens? Once you just displace that object, is there any chance that object will come back to its own position? Once it is displaced, it will not come back to its own position. So such type of equilibrium is known as unstable equilibrium. So in the case of unstable equilibrium, once the object is displaced from the equilibrium position, slightly if it is displaced from the equilibrium position, it will not come back to its equilibrium position. That is known as unstable equilibrium. For example, already we discussed, and in the case of unstable equilibrium, potential energy will be very large. Potential energy will be more because of its higher value of potential energy. Once it is displaced, it will not come back to its original position. And here, what happens again? Center of mass will be lies below the actual value. Here, center of mass lies above once it is displaced. Here, center of mass lies below once it is displaced. And in the case of neutral equilibrium, very simple, it will remain there only. Once it is displaced, also it will remain in its own position. Okay, it will be in its own position even if it is trying to displace that object. So in the case of neutral equilibrium, potential energy remain constant. Okay, and there is no variation in center of mass. Is it clear? These are all about stable, unstable, and neutral equilibrium. Okay, so today we discussed about torque and angular momentum and different types of equilibrium, translational and rotational equilibrium, and stable, unstable, and neutral equilibrium. I hope all of you understood. If you are having any doubt,